All right, so an object that's moving in two dimensions, what's interesting about this is as the object moves, let's say it's an object that's on the surface of the Earth or near the surface of the Earth. So as it falls to the surface of the Earth, gravity's pulling down on it. But what's interesting about this is there's no horizontal force acting on it. Gravity simply pulls down. So this object has a horizontal motion and a vertical motion, but the vertical motion is the only part of the motion that is affected by gravity. So what you'll notice is in the horizontal direction, the distance is the same if it's moving horizontally. So we have an initial velocity horizontally, and we have the same distance every second that passes by. So we can think of this as a motion diagram in the horizontal direction. Now the motion diagram in the vertical direction, we're going to see acceleration. So we pick up distance and then greater distance, and then the next second is even more distance, the next second is even more distance. And you can see in the horizontal direction we have constant motion, and the vertical direction we have accelerated motion. And then these points right here, this is 1 second horizontally, but this is 1 second vertically. So the object is going to be here after 1 second because we take the horizontal and the vertical, line them up, and we get the position at every second. And this is what the actual object looks like as it moves. It's going to be moving in a parabola. So again, in the y direction we have an acceleration of negative g, in the x direction we have no acceleration. For every projectile with no air resistance, we're always going to assume this. We're going to assume the acceleration in the y direction is going to be negative 9.8 meters per second squared, and the acceleration in the x direction is going to be 0. All right, so ignoring air resistance, the horizontal component of the projectile's acceleration is what? Hopefully you remember it's going to be 0 from the previous slide. Ignoring air resistance, the horizontal component of the projectile's velocity will what? Well, since there's 0 acceleration, that means it's going to remain constant the entire time. All right, so if an object is launched at some angle, so the example we just talked about was at a horizontal projection, so this object is going to be up at an angle. So it still has a horizontal and vertical component, but the horizontal component again is not affected by gravity, so it keeps that horizontal velocity the whole time. And then the vertical direction is accelerating, but the acceleration is downward. So as we go up, we're going to lose vertical speed because the acceleration is negative 9.8 meters per second squared. When we get to the very top of the projectile's path, then there's going to be no vertical velocity left because all of it's going to be 0. So, but you are still going to have a horizontal velocity. That horizontal velocity stays the same the whole time. And as it comes back down, it accelerates downward, so the downward velocity increases, and then it increases even more at the end. But notice that the horizontal velocity stays the same, but as it goes up, the vertical velocity decreases while the horizontal velocity increases. Now you notice that at position 1 right here, so velocity 1, which is this velocity right here, and velocity 3, those are going to have the same magnitude. They don't have the same direction. So the absolute value here means you drop the direction and you're just left with the amount. So the amount of velocity at both positions are the same. So as long as you're at the same elevation will always have the same magnitude of velocity. Now technically it's not the same velocity because velocity is a vector. It has to include magnitude and direction. So since the direction is not the same, the velocity is not the same, but the magnitude will be. So the initial velocity and final velocity are at the same elevation, therefore they'll have the same magnitude of velocity. So in this example, what we're going to do is we're going to figure out some interesting things about this. We're going to figure out at different points, maybe the whole hang time as it goes through. So let's talk about the horizontal velocity is going to be equal to the initial velocity cosine of the angle, and then the vertical velocity is going to be the sine component. As we have constant acceleration, the vertical direction, we have the final velocity is going to be equal to initial velocity plus acceleration times time. So the initial velocity in the y direction is sine of theta, the initial velocity sine of theta, and then in the x direction, we have a constant acceleration, I'm sorry, we have 0 acceleration, so that means that the velocity is going to stay the same the whole time. So if we want to figure out the final velocity in the y direction, then we have to take that initial velocity, subtract acceleration times time, and the final velocity in the x direction is going to be equal to the initial velocity in the x direction. And this object, it says the ball is thrown with a velocity of 20 meters per second at an angle of 60 degrees above the horizontal. What is the horizontal component of the instantaneous velocity at the exact top of the trajectory? So it says horizontal component, but to be honest, at the top of its trajectory, the horizontal component is all that's left of it. There is no vertical component. Now, if you think of the horizontal 60 degrees, the adjacent, which is going to be the cosine component, 20 cosine of 60 degrees cosine of 60 degrees is 1/2, so half of 20 gives me 10 meters per second. So the horizontal component the whole time, not just at the top, but the whole time is going to be 10 meters per second while it's in the air with no air resistance. All right, our next example, we're going to talk about the velocity in the x direction is going to be v delta x over t. So to figure out how far it moves horizontally, then we plug our velocity in the x direction into this equation, and then we multiply that that velocity times time, and that gives us the position, the displacement. We call this actually range. The distance it moves horizontally, the maximum distance it moves horizontally is the range. So the range is going to be the x component of the velocity times time. So two vectors, two components, when we add them together, remember we use the Pythagorean theorem in order to do that. So we got the velocity in the x direction, velocity in the y direction. So Pythagorean theorem, we take square root of 6.8 squared minus negative 7.4 squared, and we get a velocity that's equal to 10 units. Now I don't know what the actual measurement is. Maybe it's feet per second, maybe it's meters per second, maybe it's miles per hour, but whatever it is, the magnitude is going to be 10 units. Now what's the direction of this v, this velocity? Well, we use inverse tangent of opposite over adjacent. The opposite is going to be the y component. The adjacent is going to be the x component. So we take inverse tangent of negative 7.4, divide that by 6.8, and we get an angle of 47 degrees below the horizontal. We call that, sometimes we call that an angle of depression. So an angle below the horizontal is called an angle of depression. An angle above the horizontal, we call it angle of elevation. So we got a negative 47 degree angle or 47 degree angle of depression. All right, so in this example, define the velocity in the y direction, the displacement in the y direction. We're going to use this equation because we have a constant acceleration. We go ahead and plug in our velocity. Our velocity in the y direction equals velocity sine of theta. So we go ahead and say at this point we're going to start at 0 height. So we have our initial position is going to be 0. So this is going to be our equation for define the height at any given time. So our acceleration, negative 9.8 meters per second squared, negative g, so we get this negative g here. So this would be the equation to find that position, at the vertical position at any point. All right, soccer ball kicked with a velocity 25 meters per second and an angle of 45 degrees above the horizontal. What's the vertical component of its acceleration as it travels along the trajectory? All right, so quite honestly, you don't need to know anything about the velocity. The vertical component of acceleration is always going to be negative 9.8, so downward 9.8 meters per second squared. This next question, it says a diver is running 1.8 meters and dives out horizontally from the edge of a vertical cliff. 3 seconds later, reaches the water below. Now this 3 seconds, the time that it's in the air, we call that hang time. So the hang time is going to be 3 seconds. So how high off the cliff is this? So we're looking for that vertical direction. So we got our equation for the vertical direction. The initial velocity in the vertical direction is 0. And remember that 1.8 meters per second, that's horizontal. So there's no vertical velocity. So all we have is we have actually negative gt squared over 2. Now the negative is gone because we're going downward a negative direction. So the negative displacement and a negative acceleration, those are going to cancel. So we go plug in our values for 9.8. times 3 squared divided by 2, that gives us 44 meters for the height of the cliff. Now part B says how far from the base of the cliff does this diver hit the water? So we got the horizontal velocity, which is 18 meters per second, and since he's moving at a constant speed, we can take that speed multiplied by time, which is 3 seconds, and that'll give us our distance, which is going to be 5.4 meters. All right, so this next part, we need to figure out where the maximum height is. So how high is this object going to go? Now we're looking in the vertical direction. So to find that max height, we need the delta y. We need that y component. So we're going to use first our final velocity in the y direction is going to be 0. So we're going to get actually the time out of this equation. So the initial velocity sine of the angle minus gt is going to be equal to 0 because our final velocity in the y direction is 0. We still have a horizontal component, but not a vertical. Solve for t, then we take that negative to the other side, we get gt, and then we divide by g, and we get that initial velocity sine of theta. That's the initial velocity in the y direction divided by g. That gives us our hang time. Then we go ahead and plug that equation in for our height. To find our height, then we take their initial velocity in the y direction and then multiply by time, which is the initial velocity in the y direction divided by g, and then minus our acceleration divided by 2, and then we got initial velocity sine of theta divided by g. So when you work all this out, what you get for your maximum height, you get the initial velocity in the y direction squared divided by 2g. That gives you your max height. This question says, when a football in a field goal attempt reaches its maximum height, how does its speed compare to its initial speed? All right, so remember that an object that's moving through the air, a projectile, has two components to its velocity. It's got a horizontal and vertical component. Now, as it moves through the air, the vertical component decreases, but it still has its horizontal component. Now, since the vertical component decreases, that means the total speed is going to be decreasing as well. So the speed is going to be less than its initial speed. Now, as it comes back down and it reaches the same height at which it was kicked at, then it's going to have the same speed at that point. So the football is kicked from ground level at a speed of 18 meters per second, angle of 35 degrees from the horizontal. How much later does it hit the ground? All right, so one thing you could do is you can take the amount of time that it takes to go into the air and then double that because it comes back down. Now that would say that the time it takes to get to the top is going to be the total speed divided by the acceleration due to gravity, because what happens is as it gets to the top, it's going to stop. So gravity is going to take all that speed away. So the amount of time it takes to do that, and then you double it in order to figure out what the total time is going to be. So it's going to be 2 times that speed. That vertical component of the speed divided by 9.8 because the horizontal is not affected by gravity. Now that's one way to do it, but I want to do it a different way. The different way that I like to do it is one such that you can use at any time. It doesn't have to end at the same height that we just started at, which is what this instance right here, you have to start and end at the same height in order to use that principle. But what I would like to use is the displacement equation. So the vertical displacement is going to be equal to acceleration times time squared divided by 2. So that's the acceleration due to gravity, plus the initial velocity in just the y direction times time. So we go ahead and plug in that our displacement is going to be 0. Now this is where it's different. These two instances are different. This one just doubles the time, where this one says that the displacement is going to be 0. So the reason the second method works better is because we can have a final height that's different than the initial height, and this equation would still work. Now, if you factor out time from this, and it's going to be equal to 0, this is something that's going to be unique about having a displacement of 0. I could divide by time, which if you have a number over here, you can't ordinarily do that, but I can divide by time, I can factor that out, and I can get this equation, which is going to be the exact same equation that they had before. So just to show you a different way of how to get to it, but 2 times that speed time the initial velocity times sine of the angle divided by 9.8, that's going to give us 2.1 seconds as well. All right, so this example says, at what angle should a water gun be aimed in order for the water to land at the greatest horizontal range, the greatest range? And it's going to be a 45-degree angle. Now, the reason for this is as you have a horizontal motion, then it's not going to be in the air for very long, because there are two parts that keep an object in, two components that keep something in the air. One is a horizontal velocity, the other is the amount of time that it takes in the air, which is the vertical component. So to get your maximum range, you need to have a lot of hang time with a lot of horizontal velocity, and a 45-degree angle is going to be the perfect combination to where you have a lot of hang time, but you also have a lot of horizontal velocity. So as a projectile is fired with an initial speed of 65.2 meters per second and an angle of 34.5 degrees above the horizontal on a flat firing range. So it's going to end at the same height from which it started at. So what's the maximum height in this instance? All right, so the maximum height is going to be this equation right here. If you remember, the final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Rearranging that equation, we get this equation right here where the final velocity is going to be equal to 0. So that initial velocity squared goes to the other side, becomes negative, but then the acceleration is also negative, so those negatives cancel when you divide by 2g. Go ahead and plug in your number, 65.2 times sine of 34.5, that quantity squared divided by 2, divided by 9.8, you get 69.6 meters. The total time in the air, if you remember the equation we used before, the displacement is going to be equal to 1/2 times the acceleration times time squared plus the initial velocity times time. Plug in your numbers, factor out that t. That t is not necessary, and you get only because it equals 0. You can divide both sides by t, and then we get this equation. Plug in your numbers, and you get that the time is going to be 7.5 seconds. Part C, what's the horizontal distance covered? What's the range? Since there's no acceleration horizontally, then that means it's just going to be velocity, the horizontal velocity times time. Well, we got the horizontal velocity, the initial velocity is 65.2 times cosine of 34.5 degrees times the time, which was 7.5 seconds, and we get a range of 405 meters. All right, so relative velocity is essentially a vector addition. So when you have a velocity of the water that's going sideways, and then you got a velocity of a boat that's going across, those two velocities will actually add together. The boat's not going to go straight across because the water is moving to the east. So the total velocity of the boat is actually going to be to the northeast. So to figure out that velocity, you take that velocity to the north, and then you add the velocity to the east. Now these two velocities will give you a right angle, so it'd be easy to find the total velocity because you use Pythagorean theorem. Now when there's an angle between these that's not 90 degrees, then you have to break each one into components and then figure out the total velocity using that. All right, so in this instance, the velocity relative to the shore is going to be the velocity of the boat relative to the water, velocity of the water relative to the shore, and then the hypotenuse gives you that velocity there. So we use Pythagorean theorem to figure out that total velocity. Now, if you want to look at the distance, the ratio between the distance across and the distance downstream, that ratio is going to be the same as the ratio between the velocities of the boat and the velocity of the water, because this triangle and the triangle that you would make with L and D, they would be similar triangles. So to find the, if you wanted to find the distance downstream, you can use this, or if you wanted to, you could use the length going across, and you could divide that by the velocity of the boat. So the length divided by the velocity of the boat, that'll give you time. So you take that time and multiply by the velocity of the water, and that gives you the distance downstream. But this is another way to write it there. All right, so what if I want to angle my boat so that I can go directly across the stream, directly across the water, go from one shore to the other without going up or downstream? Well, I would have to obviously angle my boat so that I would have a component of my velocity that would be against the velocity of the water, so that I would have a net result going across the stream. So I have an angle to the northwest because the water is going to the east. So when I add those two vectors together, I get a net result directly across. So in this instance, because they make a right triangle, again, I can use this equation, and then solving for the velocity of the stream, I take that velocity of the water squared to the other side, which would be minus, and then we square root. Otherwise, you have to use the components. So you have the horizontal component and the vertical component of each vector, add them together, and then you get the resultant there. So we have our angle, and for this specific example, the angle is going to be inverse sine of opposite over hypotenuse, so the velocity of the water divided by the velocity of the boat. And obviously the velocity of the relative to the shore is going to be the distance from one shore to the next divided by the total time, and then you can find that time using this equation as well, the length divided by the relative speed with respect to the shore. All right, this question says you are trying to cross a river that flows due south with a strong current. You start out with your motorboat on the east bank, desiring to reach the west bank directly west from your starting point. So you should head your motorboat what direction? All right, so you got to have that westward component, but since the river's flowing south, you also have to have a northward component. So it's got to be somewhere in the northwest direction in order to get that westward direction that you're moving, but then countering the south flow of the water with your north flow of the north movement of your motorboat. Next question, two displacement vectors have magnitudes of 4 meters and 7 meters respectively. When these two vectors are added, the magnitude is a result of what? Now what's interesting about this is we don't know what angle these two vectors are at. So they could be in the same direction. And if they're in the same direction, they're going to be a total of 11 meters. But if they're in opposite directions, it's going to be a total of 3 meters. And if they're at some angle, then they're going to be at some magnitude between 3 and 11 meters. So the minimum is going to be when they oppose each other completely, which would be down to 3 meters. The maximum will be when they're in the same direction, which is 11 meters. But if you have any angle, then the angle is basically going to go from 3 to 5. If you think the two vectors as one hinging at the end of the other, it goes from 3 and then all the way out to 180 degrees, where it'd be a maximum where they'd be 11 meters. Next question, if the acceleration vector of a moving car is directed opposite its car's velocity vector, then what's going to happen to it? All right, whenever you have velocity and acceleration, when they're in opposite directions, the car is always going to be slowing down. When they're opposing each other, it's always going to be slowing down. When they're in the same direction, it's speeding up. When they're perpendicular to each other, that's where we get this answer for A. That's when it's going to be turning. This next one, it says a soccer ball is kicked from ground 5 times with the same initial speed. Each kick is made at a different angle above the horizontal. For which 2 kicks will the ball travel the same distance in the air? All right, so looking at this, in order to get the same distance, it's referring to range, the same range. Now we talked about how if you have a shallow angle, then it's not going to go very far because it's not in the air for very long. You don't have enough hang time. But if you have too steep of an angle, it has a lot of hang time, but it doesn't have any horizontal velocity. So a 45-degree angle is the perfect angle to get the maximum range. However, as you go up to 45 degrees, you increase your range. As you go beyond 45 degrees, you actually decrease your range. And so the 2 angles that you're going to get the same range out of are going to be angles that are complements of each other. So basically the same amount below 45 as you do above 45 will have the same range. So that's why the answer here is going to be E, 35 degrees and 55 degrees, because 35 degrees is 10 degrees below 45, and then 55 is 10 degrees above 45 degrees. So those will have the same range because they kind of compensate for their hang time and their horizontal velocity. Last question, it says a soccer ball kicked from ground with a speed of v travels a distance of d before returning to the ground. If the ball had been kicked with an initial speed of 2v, the distance it would travel would have been what? And the answer here is going to be 4d. Now the reason it's going to be 4 times the distance is because that 2v will actually give twice the velocity horizontally and twice the velocity vertically. With twice the velocity horizontally, then you would have twice the distance that would travel. But the other part of the vertical, if you have twice the distance or twice the velocity vertically, then that means twice the amount of speed that gravity has to take away and then add back. So that means it's going to be in the air for twice as long. So if it's in the air for twice as long and it has twice the horizontal velocity, if you think about the range is that the horizontal velocity times time. So twice the horizontal velocity and twice the time, that's why we have 4 times the distance for the range.